Okay, we just finished up talking about series circuit. Let's go over that one more time. In a series circuit, this is a little different one than the light bulb we had earlier, but we have a battery with a positive terminal and a negative terminal. The electrons flow. Technically, they flow from negative terminal to a positive terminal in physics because we know the electrons are flowing, and they're negative, so it starts at negative. But you will see, like on this one, if it's talking about electronics people, they tend to say that it flows the other direction. This was because I believe Benjamin Franklin originally set up the difference, and he said it was from positive to negative. That was before they knew that electrons and the negatively charged electrons were actually flowing. So you will see both ways, but at any rate, it's going to flow through the battery, through a circuit, and back to the battery again. If it's not a complete circuit, then it will stop. Any break in the circuit, like the switch here, if it's off, there's no connection, then it will stop. If one of these burn out, then it will also stop the flow, which of course is not very good. If you're using the lights and one of them go out, all the rest of them, say in the house, go off, or Christmas tree lights or whatever, that's not good at all. All right, and so that's one of the main disadvantages of a series circuit. All right, now other things about a series circuit, we said that they have the voltage. Say this is a let's say a 6-volt battery. I said it's a 6-volt battery. A 6-volt battery goes through, actually probably 12. Okay, I said 12 volt. 12 volt. If you added the voltage of each of these light bulbs, it would add up to 12. So it would divide the voltage between each of the light bulbs, and each of them would have a voltage drop of 4 volts. So 3 times 4 would make a total of 12 volts. All right. Now the resistance would be equal to the total resistance, the resistance of the whole circuit, if you will, would be equal to, get a little bigger. It's not working very good. Let's try again. All right. The resistance in this area, the total resistance is equal to the resistance of light bulb 1 plus light bulb 2 plus light bulb 3 plus however many other light bulbs you might have in this series, and the total resistance of the wire that's involved in it. Okay, and that would give you the resistance of the whole circuit. Okay, now if each of these light bulbs has a smaller voltage, they split the voltage between them, but they have part of the thing, the current going through each one of these will be the same because both of them have a same amount of resistance. They're the same type of light bulbs, and they have the same amount of voltage going through each one because it divides the voltage between the three, and so you have a steady amount of current going through each of these. All right, and since the current and the voltage stays the same, then you would basically use the same amount of power. So the current times the voltage, current same for each light bulb, the voltage is the same, and so you would, each light bulb ends up using the same amount of power. Okay, but as we said, one of the main disadvantages is if one goes out, then the whole thing goes out. You can imagine with Christmas tree lights, one goes out, you've got to go through every light bulb trying to find which one was the one that went out. So you can imagine that they began to prefer parallel light bulbs or circuits, okay, which allow, as we said in the last video, to go through as many alternate paths that it could go to get to the battery. And so if one of these light bulbs were to go out, like here, if this one goes off, then the electricity can still make a circuit here and the circle, and it does not make all of them go out. So needless to say, most of the circuits in your house, on Christmas tree lights and so forth, tend to be some type of parallel circuit. Okay, and that way if one appliance goes out or something happens with it, it does not short out all the other ones. Or if you turn off one light, it doesn't make all the other lights in the house go out. So parallels are much more common. And the main thing is, like I said, they have a separate path. There are several different paths that it can go, okay, to get through a circuit. All right, and it'll have to go through one light bulb to get back to the thing, okay? And so the voltage is the same for each device. If this were a 12-volt battery, then there would be 12 volts going through this light bulb, 12 volts going through this light bulb, 12 volts going through this light bulb, all right? And if they have the same amount of resistance as, say, a series circuit, if you have the same resistance, but now each one has more voltage, then that means there's more current, therefore you get much brighter light bulbs going through a parallel because each one's getting a full voltage instead of splitting the voltage between them. All right, and that's good news. Someone says, well, that's great because now they can all be much brighter. If you have them all on at the same time, once again, that'd be great for your house. Now, the downside of that, of course, is this. If they are all getting a full amount of current, okay, and they're getting the full amount of voltage, all right, then that means they're going to be using more power, which means this battery is going to be used up quicker. Okay, and so that is the trade-off of a parallel circuit. You can turn off one but not turn off all the others. That's good. Or if one burns out, that'd shut down the rest of them. And you have a full voltage and current going to each light bulb. However, the downside is that means it's going to end up using more power, so it's going to deplete your battery faster. All right. Now, how much current goes through each one depends on the resistance of each branch. Okay, and one of the things that happens differently in a series circuit, we said that if you take the more light bulbs you add, the more the total resistance gets to be. But in a parallel circuit, it's kind of like if you're on a highway. The more lanes you have open, then there's less resistance to the flow of traffic, because a 4-lane highway is going to let traffic flow much better than 2 lanes if you had the same amount of traffic trying to go through 2 lanes. And so when we have a parallel circuit, since we have many paths or lanes, if you will, for the electrons to travel through, then there's less resistance in each of them. Okay, and if we were to add another circuit up around the top, that would reduce the resistance in all of these circuits, and you could keep doing that. Okay, in your house, if you can continue to add new sockets, say, on to your system, and since it's parallel, then that would just lower the resistance. Okay. However, the downside to that, once again, there's always a downside, is that if you have the same voltage going through each of these, and the total resistance gets less and less and less, that means this circuit has higher and higher current. Okay. And if you continue to increase the current, it's going to increase the heat produced by that, because remember, the resistance of the wires and so forth are going to create heat, and the light bulbs and so forth. There's going to be more and more heat. And the problem is, in your house, if you keep overloading a circuit and keep adding more and more things to the circuit, or things that require too much power, eventually the circuit is going to get so hot that it could cause a fire. And so you need some kind of safety device to keep that from happening. All right. In older homes, you would have a screw-in circuit fuse like this. And basically, this would be in your circuit box, and you would have the electricity that's going in the circuit would go through this fuse first. And if it's too high, if it gets too high because you have too low resistance, because you've plugged in too many things, then it would heat up this little piece of metal here, and it would break, and that would break the circuit. Okay, and that's basically what a fuse's job is. But since this has melted this piece, you can't fix this fuse. You have to get another fuse and put it in there. Now, because of the shape of this one, people could put a penny in there, and it would connect these two and allow circuit to go through, which keeps your lights from going out. But the bad news is, since it's still getting hotter and hotter and hotter, if it's overheating, it's still going to overheat, and now it may actually cause a fire. Your fuse is a safety device to stop that from happening. All right. Now, there are other types of fuses. If you look in electric, like we have some electric multimeters we'll use, they usually have some type of fuse like this. You see this silver's in, there's a silver piece of metal in the middle, and that's what would melt and break the fuse. Okay. In your car, you would find some that look more like this. Okay. They plug in usually kind of underneath your steering wheel and stuff like that. Also, there's some underneath the hood sometimes. But basically, when the circuit goes through, you have this little loop of metal in the middle, aluminum or some other type of low melting, that melts at fairly low temperatures. And if the circuit current gets too great through here, it breaks that, and that helps protect the circuit from getting too hot and catching on fire. Now, the problem with the fuse is it has to be replaced, and that's why people went and used to put pennies in here, but that kind of defeats the purpose of the safetiness of it. So instead, in your house, you usually have circuit breakers, okay, or circuits, okay. And this would be, if you go look in your breaker box, okay, somewhere in your house, there's a breaker box, and it would look something like this. and you would be seeing the part out here with the switch of these, and they would be however many amps. And say it's a 15 amp, that means if the current gets greater than 15 amps, and this would turn itself off, it would flick the switch. Okay, and you only have to go back and flip the switch back on, and it will allow electricity to go through it. Now, if you haven't fixed the problem, it will just keep switching back off. Okay, but say we had a big electric grill outside, and it was just over, and it's on the same circuit as the microwave, which is on, and the refrigerator. As long as I leave all those things plugged in, it's going to keep knocking the circuit off. But if I unplug, say, the grill, or don't use the microwave at the same time, then I could switch this on and it would be okay. So the nice part about a circuit breaker is that it is reusable. Okay, here's just one what it actually look like. Usually they're black. They can be one or double wide like this. And so the nice part is they can be switched back. You don't have to replace them. They aren't destroyed, as a fuse is destroyed once you use it. Last couple things about a circuit breaker. One, when the current gets too strong, how does it switch off? Well, basically, the current, the electrical current, creates a magnetic field. That magnetic field pulls the switch, or pushes it, depending on how you look at it, and it creates an attraction that pulls it off. Okay, and we'll talk more in the next chapter about how electricity and magnetism are tied together, but that's basically what would happen. This would be your circuit box, and hopefully you would have labeled what each one of these, not usually, in my experience, it's not really the way most ones have been done, unfortunately, but it's nicely labeled with numbers here, and they say exactly what they go to over here. So say you want to wash on your dishwasher, you would come turn the circuit off, and then you could go work on your dishwasher without worrying about being shocked or you shut off the electricity to it. Okay, so it's used by magnetism, and this is your circuit box, which will allow, or circuit breaker box, which will allow you to turn off circuits if you want to work on something on that circuit. Now, the last thing is having to do with water. We know water and electricity do not mix very good. Anywhere in your house within so many feet of a sink or water source, bathtub, so forth, is supposed to have one of these, and these are ground fault circuit interrupters. So these are called, for short, GFCI, ground fault circuit interrupter. And say, for example, you were, there's a short circuit in your hair dryer. I don't have to use that very much, but say you're using a blow dryer to blow your hair. If there's a short circuit, it might seek to go through your hand down to the ground rather than going through the circuit, and you have short circuit and you would receive a shock. So the purpose of this is you have two outlets, each plug, and it basically monitors the amount of circuit going out and the amount of circuit going in. And if some circuit's being lost somewhere, which means there's some kind of a short or something being given off and could be dangerous, shocking somebody, then it will shut off the circuit. And they have these little reset buttons and test buttons to see if they're working. And once they shut off, you may have to go back and reset them and open them back up again. But their job is, if they notice there's less circuit coming back than is leaving, then they will shut off, because obviously some of that electricity is being lost somewhere, and it could possibly be shocking you. And so it really protects you against short circuits. And anywhere that, since water, it's a possibility if the cord's in the water or something like that could cause that, that's why they have to be in houses anywhere near some type of outlet. But those are all safety devices to help us from being electrocuted by our electricity. That concludes our lectures for electricity. See you on Thursday, and our next chapter will be magnetism, which is related to electricity. Have a good day.